So welcome back. So I am currently trying to show that if you have two gamma random variables, x and y, that are independent and which have the same beta parameter, then if you consider a third random variable which is obtained by adding the two together, then it is going to be gamma distributed with parameters. You take the two alpha parameters and add them together and you keep this same beta parameter that was common to both of them. That's what I'm currently trying to prove, and my strategy for doing this is to find the moment generating function of this third random variable, which is the sum of the two. And I've said because they're independent, it's going to be the moment generating functions of the two initial random variables, x and y, multiplied together. And then once I've found the moment generating function by finding these two things, moment generating functions, and multiplying them together, I'm going to go backwards and get to the distribution, therefore, that x plus y must follow. And that bit is where I'm going to probably pull the wool over your eyes a little bit, because we won't properly justify why there is a one-to-one correspondence between MGFs and PDFs. That involves some quite serious analysis, which is beyond the scope of this video. But if you believe that, and I'm sure you've probably seen this approach used before, then from the MGF of this thing, we will be able to realise that it must be distributed in this way, because we'll see that its MGF is one of these MGFs of the gamma distribution. So currently, we're trying to find for a gamma distribution what its MGF is going to be. Obviously, that's going to be really important to us because firstly, we need the MGFs of these two things so that we can multiply them together, and then we need to recognise that this product is itself an MGF of a gamma distribution. So let's think, for a general gamma distribution, what is its MGF? So let's take S, a random variable, I'm just call it S, and it's going to be gamma distributed with parameters alpha and beta, and let's think, what is its MGF going to be? So by definition, the MGF of this random variable S at t is going to be the integral from 0 to infinity of e to the tx times the PDF of the gamma distribution. So I've pulled some of the constants out, so we've got beta to the power of alpha over gamma of alpha, x to the power of alpha minus 1, e to the negative beta of x, dx. So we need to perform this integral, and what we get will be a function of t, and that will be our MGF. Now, this integral isn't going to be defined for all values of t, so it's only going to be a function on the values of t where this integral actually converges to something and exists. So just now, having a bit of a fiddle around with this integral, so I've still got the constant out the front here, we've got the integral from 0 to infinity, and now I've combined this exponential with this exponential, so the polynomial bit is still here, x to the power of alpha minus 1, and now I've got e to the negative beta, and then I've put the t in a bracket with this minus out the front, so that means that the t has now got a minus in front of it, so it's minus beta minus t times x. So hopefully you can see that if we multiply this bracket out, we'll get e to the negative beta x plus tx, and that's the same thing as what we've got here. And the reason I've done that is because this integral, in order for it to converge and be something finite, we need this to be a negative exponential here. If it's a positive exponential and we're integrating off to infinity, then it's just going to go out of control and it's not going to converge to something finite. So we absolutely need this to be a negative integral, which is why I've got this minus out the front. So we need this number in the bracket, therefore, to be positive, because if it's negative, it will cancel with this minus and you'll get a positive exponential here for the positive real numbers. So we need beta minus t to be greater than 0, and we can rearrange that to t therefore needs to be less than beta. So this is the range for our t value. This is where it's going to converge. If t is less than beta, then the MGF will be defined. If t is greater than beta, it won't be defined. For t is equal to beta, it also won't converge to something, because if we make t equal to beta, this will go to 0, so this will just go to 1, so all we'll end up with is x to the power of alpha minus 1. If we integrate that, we'll get x to the power of alpha over alpha. Alpha is a positive number, remember, always in the gamma distribution. Both the parameters have to be positive numbers. Therefore, you've got x to the power of a positive number, and if you take the limit as that approaches infinity, that will go off. So this moment generating function then is only going to be defined on this range where t is less than the beta value. So for these values of t that are less than beta, how are we now going to actually work out what this integral is to find out what the value of the function for a given value of t in that range is? So it's time for a brilliant trick, and the brilliant trick is to realise that what we've got here looks very much so like a PDF of a gamma distribution, and it looks like a gamma distribution still with parameter alpha, but now with beta parameter, not beta, but beta minus t. Now there's an opportunity for a little bit of confusion here. T, with respect to this integral, is not varying. It's a constant. Now you might think, but t is a variable here. Surely t is something that's varying. Well, as a part of the bigger function, this moment generating function, yes, t is a variable, but once you've chosen the t that you want to evaluate the moment generating function at, it's then given by this formula. You have to plug t in here and work out this integral. So with respect to this integral, t is not a variable, so t is something that is fixed with respect to this integral. So we are integrating something that looks like the PDF of a gamma distribution with parameter alpha and beta parameter beta minus t, and beta minus t is a perfectly good parameter for the or perfectly good beta parameter for the gamma distribution because it's greater than 0. Remember, these two parameters always have to be greater than 0 in the gamma distribution. So we know that if we integrate the PDF of a gamma distribution over 0 to infinity, it comes out as 1. So all we need to do is make sure that the right constants are in front of here, and the right constants aren't quite in front of here. This one's right, but you would need a beta minus t to the power of alpha. So that's what we're now going to do. We're going to multiply top and bottom of this fraction by beta minus t to the power of alpha. So that gives us this. Here is the beta to the power of alpha, it survived. Here is the gamma of alpha, it survived. But now I've got beta minus t to the power of alpha here, and I've also got beta minus t to the power of alpha here, so they would cancel out. And then we've got the integral from 0 to infinity of what we had here, x to the power of alpha minus 1 e to the negative beta minus t x dx. Now this thing here, ignore this bit here, all of this, if you pull this inside here, this and this is the PDF of a gamma distribution with alpha parameter alpha and beta parameter beta minus t, and we're integrating that PDF from 0 to infinity, so that has to come out as 1, so all of this bit is just going to equal 1, so we're just going to get 1 times this, so we now know what our moment generating function is. We've got rid of the integral. So our moment generating function then for our random variable s, which is a general gamma random variable, is given by this. It's beta over beta minus t all to the power of alpha, and that's valid on the range t is less than beta. So here's the real line, here's 0, here's beta, which is some number greater than 0. It's valid on all this part of the real line. It's not valid at beta, and it's certainly not valid for these these numbers, positive real numbers that are greater than beta. But on this part of the real line, it is defined, and that's what it is equal to. So now back up to here then. So we were trying to work out the moment generating function of our random variable x plus y, and we said because x and y were independent, it's the moment generating function of x times the moment generating function of y. Now x is gamma distributed alpha 1 beta, and y is gamma distributed alpha 2 beta, and now we know what the moment generating functions for a gamma distribution is. So this one, the moment generating function of x, is going to be beta over beta minus t to the power of alpha 1, and this one, the moment generating function of y, is going to be beta over beta minus t to the power of alpha 2. Remember, they share a beta, and both of these moment generating functions are valid on the range t is less than beta. So that means that our overall moment generating function of the random variable x plus y is going to be these two things multiplied together, and it's also going to be valid on t is less than beta. But you can see how we can join these together quite easily. We've got the same thing raised to different exponents here, so we can just add the exponents together. So doing that, we get that the moment generating function for x plus y is going to be beta over beta minus t to the power of alpha 1 plus alpha 2. So I've added these together, and that's going to be valid on the range t is less than beta. But now you can see that that is the moment generating function of a gamma distribution where the alpha parameter is alpha 1 plus alpha 2 and the beta parameter is beta. And this is the bit where we're not going to prove it. So we're going to now conclude, therefore, that x plus y, as its moment generating function is this, and such a distribution would have this moment generating function, that therefore x plus y must be distributed in this way. Now that is true, but that is a major theorem that we are not going to prove here, which is that if you have a moment generating function, there is only one distribution with that moment generating function, that there is a correspondence between PDFs or distributions and moment generating functions that is 1-to-1. That is a serious bit of analysis to prove that, and we're not going to do that. But that is true. So by the fact that x plus y has this moment generating function, and that is the moment generating function that such a distributed random variable, gamma distributed random variable with these parameters would have, we can therefore conclude that x plus y must be distributed in this way. So overall, I hope I've given you a decent enough argument as to why, if x and y are independent and x is distributed gamma alpha 1 beta and y is distributed gamma alpha 2 beta, where this beta is the same for both of them, then if you consider the third random variable, which is the sum of the two, that it will be gamma distributed alpha 1 plus alpha 2, and then the beta parameter stays the same. And now that we've got that, I've therefore given you the argument as to why, when we add together these n independent gamma a half distributed random variables, we will therefore end up with a random variable that is distributed gamma n over 2 a half. So therefore we can conclude that the chi-squared distribution with n degrees of freedom is just a special case of the gamma distribution, namely gamma with alpha parameter n over 2 and beta parameter a half. And with that, we will finish this video here. Thank you for watching.